We'll now discuss the network layer. The first two layers of the protocol stack enable us to transmit messages from node A to node B, but this is only if the two nodes are directly connected by a physical link. And as we know, there's a lot of nodes that aren't directly connected. So it's the job of the end-to-end network layer to deliver a message from the site to where it was created to its ultimate destination. So the network layer is what's in charge of making sure that a message gets sent from the sender and it actually arrives to the destination. So to accomplish this delivery task, every node must agree to the same addressing scheme. That way everyone is able to identify that final destination. Thus, there are two critical responsibilities of the network layer. So the first one is to create a universal addressing scheme for all network nodes, and then delivering the messages between any two nodes in the network. Every node in the network must run the identical network layer protocol, and it's one of the most important parts of the protocol stack. So the network layer in the internet is actually called IP, or Internet Protocol. Now, you've probably been exposed to the host naming scheme that's used on the internet. So, I mean, you probably use it in your emails or whenever you go to websites. So, like, for example, you might go to a site like google.com or wvu.edu. So those are host names. However, these host names are not the actual names that the nodes use to identify each other in IP. Instead, the nodes identify themselves by using a 32-bit IP address. And this is broken up into four 8-bit numeric quantities that's in the range of 0 to 255. And each of these would be separated by a dot. Just to give an example, an IP address may be something like 141.140.1.5. So humans would read the host name, but the machine would read the IP address. So each part here would be converted into binary in this case. So the machines would read the IP addresses, but we would read the host names. And the host names and IP addresses correspond to the same thing. Now, it's the task of a special internet application called the Domain Name System, or DNS, to convert from a symbolic host name, such as like wvu.edu, to its equivalent 32-bit IP address. So think of this DNS as this huge, massive database, and it's distributed over literally thousands of machines that contain, where if you put them all together, contain all of the host name to IP address mappings for however many host computers there are on the internet. So the whole point here is that whenever we use a symbolic host name, the character string would be forwarded to a computer, which is called a local name server. And this server would check to see if it has a data record containing the IP address for this symbolic name. And if so, then it will return a corresponding 32-bit value. Now, if it doesn't, if it cannot find that name and IP address, the local name server would forward it on to a remote name server. And then maybe it'll forward it to another one and another one and another one. It'll just keep going until it locates the name server that knows the correct IP address. When we actually send a message, the network has to select a path along the nodes to get to the destination. We did a couple of examples of this before about trying to send a message from one node to another. And this is what we call routing. Now, as far as trying to determine the actual path that we want to take, I mean, there are different types of routing algorithms out there, but they all prefer what we call the shortest path or the best path. Now, when we talk about shortest path here, we're talking about the shortest path between two nodes, and it's not necessarily the shortest path in length, but rather how fast the message can travel. So we're looking for the quickest route in terms of the time it takes to send that message. Now, the thing we're going to be very careful with is the network is very large, so we need to come up with a very efficient approach for trying to find the shortest path. If we just try to check all possible paths, that's going to take forever. We can't just check every single path and pick the smallest one. We need something a little bit more efficient. And there are some algorithms out there that do this. One example is Dijkstra's algorithm, which we're not going to get into in this class, but it's a very efficient algorithm for trying to find the shortest path from one place to all other possible destinations. And the other thing we have to keep in mind when trying to determine the path is that networks are dynamic because nodes will come online and offline all the time. So that means the routing must adapt very quickly. So if a node goes down, the routing algorithms have to find an alternative route in order to get to its destination. We'll now talk about the transport layer. Let's say you're trying to send a letter to someone in a building that has a whole bunch of people in there. Now you might include the name and maybe the name of the building, and that gets you so far. But that might not be enough because there's so many people in that building, you might need to be more specific with like the room number or the floor. So usually when we send something to a particular person that's in a big building like this, we would normally include that additional information about like what floor, what suite, what room, and so forth. And the same thing is true for the internet. Just because every host computer has an IP address, that may not be enough. Sure, the IP address will uniquely identify the machine, but there are a lot of programs that are running on that machine that just kind of does its own thing. So when a message comes in, how do we know which application or which program is supposed to get that message? So we need a way to do that. The IP address alone is not enough to determine which program should be getting this message. So we need a second level of address that identifies not only a specific machine, but also the specific program on that machine. And this program identifier, which we usually denote with a small integer, is what we call a port number. So we use this to uniquely identify the program that we want to send the message to. So it's similar to the address that we were talking about before. Now, assigning port numbers to programs and remembering which program goes with which port is part of the transport layer protocols. So, although each host computer has an IP address, it may have, at any moment in time, many active ports. So the purpose of the transport layer protocol is to create this program-to-program delivery service. So the idea with this is that we would actually move messages from one specific program at a host to another specific program at the destination. So it's not that we're just moving it from one host to another. We're trying to figure out once a message is received, which program should actually get it. And this is done by taking a look at the port number and then figure out which program is associated with that port number. Now, all of the important applications that use the internet have well-known port numbers. On every single machine, the port numbers for specific programs are the same no matter what. So let me give you just a couple of examples. We're not going to go through every single one. We don't have time for that. But I'll just give you a couple of common ones. So like a web server, for example, will be port 80. So anytime that you are going to a web page, although you're not explicitly typing it, you are looking at port 80 when you go to a particular web page. The DNS server that maps the host name to the IP address is port 42. And then whenever we do something with email, or SMTP is the actual protocol name, so whenever you're doing anything with emails, you're actually using port 25. Now, there are, like I said, there are many other ports out there. There are things for like exchanging files, there are things for printing, there are things for all sorts of types of communications. But the whole point we're just trying to get at is that every program that involves some type of network connection has a unique port number, and some of them are standard among all computer systems. On the internet, the primary transport protocol is the TCP, which stands for Transport Control Protocol. Now, TCP requires that the two programs at the source and the destination nodes initially establish a connection. So before we can actually send anything from one machine to another, we have to establish a connection ahead of time. So that means they must first inform each other of the fact that there's going to be a message exchange between them. And they must also describe the quality of the service that they want to receive. Now, this connection does not exist in the hardware sense. There's no wire that's physically connected to them. But this is more of a logical connection that exists. So we send this small message, small notification that says, hey, this host wants to send a message to this host. Now, once this connection is established, then the messages can be transmitted from the source program to the destination program using the data link protocol that we just talked about. So it would actually connect to all the different hosts to send that message. So this is going to use the same ARQ algorithm that we've talked about before. So if the message is lost or something goes wrong, the source isn't going to receive the acknowledgement, so it'll eventually send it again. So it'll keep doing this until the message is actually sent across all the hosts that's necessary to send the message. So what this does is it actually ensures that the message is eventually delivered to the application program that waits for it. And therefore, this TCP connection does function like an error-free channel. So we're trying to make sure there aren't any errors in the message and the messages are received in the proper order.